Washington's Rattlesnake Ridge landslide, an active crack in the mountain, has become a geologist's laboratory. Since October 2017, a giant fissure has opened in Rattlesnake Ridge near Union Gap, south of Yakima, Washington, and a massive block of rock and soil has been slowly sliding downhill along it. What exactly is moving and why? Could this slow slide suddenly turn into a catastrophic collapse? Experts have tracked every centimeter of motion. In plain language, this is not an earthquake speed event. Instead, it is a colossal translational landslide, essentially a huge, rigid slab of basalt rock sliding on a buried, weak sedimentary layer. Monitoring data and geological studies show the mountain has been creeping at a nearly steady rate, not accelerating to a quick failure. This story dissects the mechanics, the setting, the geometry of the slide, its size and speeds, and why scientists think the mountain will continue to creep rather than fall apart all at once. Geologically, Rattlesnake Ridge is part of the Yakima Fold Belt, a series of long east-west ridges formed by folding of Miocene-age Columbia River basalt lava flows. In this area, hard basalt layers are interleaved with softer sediments. On the slope above Interstate 82 and above a gravel quarry, a mass of about 4 million cubic yards, roughly 3 million cubic meters, of these basalt flows is sliding southward on a weak, silty interbed that dips only about 15 degrees toward the quarry. In other words, picture a giant block of fractured basalt, essentially one piece, gliding along a nearly parallel weak layer beneath it. This configuration makes it a classic translational slide. Rather than breaking into many pieces or flowing like wet mud, the slide moves as one block or a few large blocks, like a table slipping on an inclined, lubricated plane. State geologists describe it as blocks of basalt sliding on a weaker sedimentary layer. The slide first attracted attention in October 2017 when aerial photos and a local pilot revealed large parallel tension cracks opening in the ridge surface. These cracks, one reported as about 200 feet deep, mark the head and flanks of the moving block. Over the next months, additional fissures appeared and existing cracks widened. Although dramatic to see, these cracks are the natural result of the block peeling away from the ridge behind it. Importantly, they are not new tectonic faults. They simply show where the mountain is pulling apart under gravity as it slides. How fast is the mountain moving? Geodetic monitoring, including global positioning system measurements and laser scans, has quantified the motion. At its peak, in early 2018, parts of the landslide were moving on the order of a half meter per week, roughly 1.5 to 1 7/10 feet per week. In more familiar units, that is around 45 to 50 centimeters per week, or about 6 to 8 centimeters per day. If sustained, which it has not been, that would be on the order of 25 to 30 meters per year. These rates were measured between January and April 2018. By mid-2018, the slide had already slowed. It was moving only about 2/3 of a foot per week, about 20 centimeters per week, by May. By the end of 2018, the fastest sections were about 8 inches per week, about 20 centimeters per week, and much of the block was slower. For perspective, 8 inches per week is roughly 1 centimeter per hour, a snail's pace by earthquake standards, but astonishingly fast for a rock slide of this scale. Crucially, scientists saw no runaway acceleration. Early in the slide in late 2017, the motion did pick up from about 1 foot per week to over 1.5 feet per week, and analysts used that for worst-case failure forecasts. But by January 2018, the slide settled into an almost constant velocity. One independent engineering report notes that after initial acceleration, movement virtually stopped accelerating and leveled off at about 2.5 to 3 inches per day, roughly 6 to 8 centimeters per day. In effect, the landslide has been creeping along at a steady rate, not speeding up toward a cliff. By the end of 2018, the Pacific Northwest Seismic Network confirmed the trend. The fastest part of the slide had fallen from about 1.7 feet per week to only about 0.8 feet per week. In other words, the sliding block gained momentum early on, but then largely decelerated to a slow crawl. While the block has been sliding downhill, the tension cracks have been opening laterally by tens of centimeters per week at the peak of activity. Unmanned aerial vehicle surveys and laser scans found cracks widening roughly 30 centimeters per week, about 1 foot per week, during the most active period. This simultaneous opening and sliding is typical of a block rotating slightly and shedding material into the open space. However, even these widening rates slowed as the motion eased back. Throughout 2018, new cracks kept forming at the crown of the slide, and existing fissures grew, but at diminishing rates as the hillside adjusted. Just how big is the moving mass? The slide area is on the order of 20 acres, about 8 hectares. The total volume of rock and soil involved has been estimated at roughly 3 to 4 million cubic yards, or about 2.3 to 3.1 million cubic meters. Washington Department of Natural Resources fact sheets and engineering studies both put the volume near 4 million cubic yards, about 3 million cubic meters. Some early news reports cited 1 million cubic yards, but that appears to have been an underestimate. To visualize that is comparable to a cube hundreds of meters on a side, an enormous chunk of mountainside in motion. When such a block creeps, its entire headscarp and lateral edges are exposed, giving the appearance of a mountain splitting open. What is driving the movement? Geologists attribute the slide to the slope geometry and rock structure, not to a trigger like a heavy storm or earthquake. The key is the weak sedimentary layer underlying the basalt block. This layer, part of the Ellensburg Formation siltstone unit, dips gently toward the quarry at about 15 degrees. Gravity is pulling the overlying basalt downward along that plane. Since the dip of the layer is shallow and roughly aligned with the ground surface rather than cutting steeply through it, the block is free to slide like a huge board. Instrumentation shows that the slide plane is fully mobilized. After roughly 12 feet, about 4 meters of displacement, the block is essentially free at the headscarp and sides. In fact, engineers note that available buttressing at the toe or flanks is nominal and decreasing, meaning the block is barely held back by anything. Friction on that sedimentary plane is the only thing keeping the block from surging downward. Importantly, that slip surface appears to have reached residual shear strength, the lowest level of frictional resistance. In short, the block is riding on a nearly bare, weak layer. Under these conditions, the forces on the slide mass will not change dramatically, so its speed will not suddenly jump without a new stimulus. Are external factors involved? Not in any obvious way. The Yakima area is semi-arid. Water does not seem to be lubricating this slide. State agency reports explicitly note that water does not appear to be a factor in the Rattlesnake Ridge movement. The region gets only a fraction of the rain that triggered Washington's deadly Oso slide, and the rock here is consolidated basalt, not saturated clay. Engineers and geologists have not identified heavy rainfall or snowmelt as a cause. Similarly, there is no evidence of a recent earthquake triggering this. Seismic monitoring has focused on the small signals from internal cracking, but no external jolt is implicated. Instead, the slide likely reactivated an old failure surface. Mapping shows the anticlinal fold here had been recognized as landslide-prone on geologic maps. Over the decades, quarrying and gradual erosion might have chipped away at the balance, but the actual motion has behaved like a natural process of slow gravitational adjustment. How has the motion been measured? Local agencies installed an array of GPS stations and total station prisms on the slide body, and analysts have monitored changes weekly or even daily. As of January 2018, one map showed vectors up to about 2.5 inches per day downslope in the fastest zone, which is about 6 to 7 centimeters per day. A radar-based map from May 2018 labeled the movement at about 1.5 feet per week, roughly 45 centimeters per week in places. Over the following months, those rates fell roughly in half. By late 2018, the block's speed was measured in inches per day rather than feet per week. For ongoing context, researchers also recorded microquakes, up to a few hundred per hour, emanating from the slide. These weak signals just confirmed the many tiny internal shifts within the mass and generally declined in frequency as movement slowed. What is likely to happen next? The consensus is to keep monitoring and let gravity take its course. All indications are that the slide will continue to creep slowly southward and southwestward, feeding debris into the quarry below. As it does, rockfall will accumulate at the toe of the slide and in the quarry pit. Indeed, observations show a growing talus pile against the quarry wall. Over time, this pile could act as a natural buttress, a wedge of accumulated debris that might gradually lock the block in place. In plain terms, the moving block is expected to run into its own rubble. The engineering review makes it clear that the slide is predicted to settle into a slow creep, on the order of a few inches per week, for years or even decades. Even after a year of detailed study, no one can predict an exact outcome, but the most probable path is this long measured slide, not a sudden collapse. As the Wiley and Norrish review puts it, the landslide will continue to displace for an indefinite period at a slow and deliberate rate, and the chance of a rapid large-scale failure is deemed very improbable. In a nutshell, Rattlesnake Ridge's giant crack is not like the swift mudslides that burst forth after storms. It is the slow unwinding of an old water-starved translational slide. Think of the block like a massive shelf of rock inching down a slope, tens of centimeters each week, with its top edge tearing open at a similar rate. That is extremely fast for a landslide of this size, but geologically it remains a creeping event, not a cataclysm. Scientists continue to watch it closely with GPS, lasers, and even seismometers, partly because such clear measurements of a big slide are rare. Each centimeter recorded in Washington now helps inform future warnings of creeping slopes worldwide. For now, the lesson is that even huge mountain blocks can sometimes slide subtly without drama until nature gradually stabilizes them again.